Welcome to part 2 of my lecture series on the multi-grid method. In this part of the lecture series, I'm going to be talking about the methods that are used to transfer between levels in the multi-grid. We're going to be looking at how we can move down a level from the original mesh down to a coarser mesh, and also how we can move back up a level again, back from that coarse mesh to the original mesh. I'm going to be using some simple examples that you can follow along with at home, and they're really going to solidify your understanding of the method so you can go back to the CFD user manuals and the literature and really understand what's going on. Right, if you're excited for this talk, let's get into it and look at the methods that we can use to move between levels in the multi-grid method. So let's start things off with a quick recap of the multi-grid method that we covered in part 1 of this lecture series. The first stage in the multi-grid method is to do a few iterations of the Gauss-Seidel algorithm to remove the high frequency components of the error. So that's the high frequency spatial variations of the error. And if we plot along a line through the previous example problem we considered, we can see that through iteration 1 and iteration 5, we've got some of these high frequencies where the error varies between adjacent cells. And then after a few iterations, those high frequency components have been smoothed out. We just have a smooth error field, which then reduces as we carry out more iterations. What we then do is, when we've done a few iterations to remove the high frequency components of the error, we stop and then we calculate the residual vector using the current solution. We substitute in x to equation 1 and calculate the residual at the centroid of all of the cells in the mesh. And that residual vector now becomes the source term in the update equation that you can see there in equation 2. So we've stopped Gauss-Seidel on the original equation ax equals b, and we've now switched over to the correction equation and we're solving a delta x equals r instead. And once we've solved this equation, we've calculated delta x, we can then apply delta x to the solution x, and that will give us the new solution for our solution vector x. And the idea we introduced at the end of the previous lecture is we want to solve the update equation on a coarser mesh because the low frequency components that we have on the original mesh become high frequency, so they're easy to remove with the Gauss-Seidel algorithm, and also iterations on the coarser mesh are faster because the matrix equations are smaller. But the big question is, of course, how do we transfer this equation a delta x equals r from the original mesh down onto a coarser mesh? And this process is generally called agglomeration in the finite volume method. The fine cells in the original mesh are combined together. They're agglomerated together to form bigger cells. And this allows us to move from the fine mesh to the coarser mesh. And for this kind of mesh, for example, it would be easier to see that we could combine 4 cells that are next to each other together into a larger cell, and that would allow us to define what this coarser mesh is. The reason we need the CFD code to do this, of course, is we don't want the user to have to feed the CFD code multiple different meshes. We want the CFD code to be able to do this agglomeration process, combining the cells together to make coarser cells by itself. The user should never have to know what the CFD code is doing under the hood. Of course, on this coarser mesh, once the cells are agglomerated together, rather than having 64 cells in this example mesh, we've now only got 16. So that means the matrix equation is actually different. Rather than solving a delta x equals r, we've actually got a new equation, a prime delta x prime is equal to r prime. The meaning of the terms is still the same, but the dimensions of the matrices are different. So the A matrix, for example, was originally 64 by 64 on the original mesh, because we've got 64 centroids in the mesh. But on this new coarser mesh, this A matrix is now only going to be 16 by 16. So we somehow need to change the size of the matrices when we move to the coarser mesh. And this needs to happen without the user's input. So I'm going to address this question of transferring from the fine mesh to a coarser mesh in terms of how do we set up r prime a prime on the new mesh, and when we've calculated delta x prime, how do we transfer that back to the original mesh? And you can probably guess from this that we're going to have to do some kind of an operation to change the size of our matrices and vectors to move between meshes. So rather than thinking in terms of changing meshes, I want you to think in terms of changing the size of the matrices and vectors, and that will allow us to move between meshes. And the first quantity I'm going to look at is I'm going to look at the residual. So how do we change the source term, the residual, from the original mesh to the fine mesh? How do we go from R to R prime? This process is called restriction in the multi-grid method literature. And in order to understand restriction, we need to think a little bit about what the residual physically represents. And if we were solving a matrix equation AX equals B that represented conservation of energy, it was the energy equation, the key thing to remember is that the residual represents the energy imbalance. So each entry in the residual vector, R1, R2, all the way down to Rn, represents the energy imbalance in each cell in the mesh. So of course it's going to have 16 entries. Each of those entries is going to be the energy imbalance in a cell in the mesh. And each of those entries has units of watts. Of course, this makes sense. As our solution converges, the energy imbalance in individual cells will tend to zero, and when our energy imbalance is equal to zero, conservation of energy is satisfied. We have AX equals B for each of the cells in the mesh. So what does this mean? How does this physical understanding help us when we want to do restriction? Well, if we think physically about combining cells in the finite volume method, if we have this example mesh with 8 cells, and I want to combine these top 2 cells in the left into a larger cell. My cell on the left has an energy imbalance of 3 watts, and my cell on the right has an energy imbalance of 2 watts. That means there's 3 watts of power, 3 watts of power coming out of that cell. There's 3 watts more coming out than going in. So there's a 3 watt imbalance in the left cell, and there's 2 watts more coming out of that cell on the right than there are going in. So when I combine these 2 cells together, the energy imbalance for the region that's enclosed by the volume is of course going to be the sum of 3 watts and 2 watts, because this region on the left is producing 3 watts more of energy than it's taking in, and the region on the right is taking 2 watts more than it's giving out. And the cell represents the contents, the energy that's contained within it. So that means for the residuals, we need to sum the residuals together when we agglomerate those cells together. And this process is called restriction. Now, we may not, of course, be solving the energy equation. We may be solving a different equation in the CFD code. If we were solving the U momentum equation, for example, again, we'd still have the same residual equation, but in this instance, the residual for the U momentum equation doesn't represent the energy imbalance, it now represents the force imbalance in the x direction. So each of the entries for the residual vector represents the force imbalance in a particular cell in the mesh, and each of those terms will have units of newtons. So for example, if we think back to that 8-cell mesh and we want to combine the top 2 cells there, this cell on the left has a force imbalance of 12 newtons. So there are 12 newtons more moving out of the cell, or the cell is applying 12 newtons on surroundings. More than 12 newtons is being applied to the cell. And the same for the cell on the right. There's a 15 newton imbalance in the x direction. So when we combine these 2 cells together, the force imbalance is now 12 newtons plus 15 newtons. That region of space that's enclosed by the cell has a force imbalance of 27 newtons. So just from these previous 2 examples, you can see that regardless of what our linear algebraic equation actually represents, when we agglomerate the cells together, we're going to sum the residuals, regardless of whether we have the energy equation or the momentum equation. And I wanted to make the very important side point that this process of restriction, where we sum the residuals, only applies in the finite volume method, and that's because in the finite volume method, the matrix equations physically represent conservation laws for different quantities. And this is slightly different to the finite difference method or the finite element method. When you do agglomeration in those 2 methods, you may have to do a different approach for restricting the residuals. but most modern CFD codes use the finite volume method, and so for us and our understanding, when we agglomerate those cells, we just need to sum the residuals together. So now we've got that physical understanding, how is that actually applied to the vectors and matrices? Now, if you look at the example problem I've got here on the slide, let's say we have an original mesh with 6 cells, and we decide to agglomerate cells 1 and 2, cells 3 and 4, cell 5 and 6 together to create this new coarse mesh, which have cells 1', 2', and 3'. We now know physically that for the residual vector, we need to sum the residuals of the cells that are agglomerated together. So cell 1 and 2 will be agglomerated, 3 and 4, and 5 and 6. But ultimately what we need to do is we need to go from this residual vector R that has 6 entries, because there are 6 cells in the original mesh, into a new residual vector R prime, which now has 3 entries. We need to change the size of our vector, and we need that changing size process to reflect the restriction that we've just gone through. So how do we do this mathematically, and what will the CFD code actually do? Well, let's just look at a simple example. This is the easiest way for us to understand. If we look at cell 1' in the coarse mesh, for example, the residual in this new cell, R1', is just going to be the sum of R1 and R2, because those are the cells that are agglomerated together. The same for cell 2', R2' is just equal to R3 plus R4, and R3' is just equal to R5 plus R6. So this is what we're doing. We're physically combining the residuals for the region of space that's enclosed by the 2 cells that make up the new cell. And we've now got 3 linear algebraic equations. We can actually write these linear algebraic equations in matrix form. And this is the part that I really want you to focus and pay attention on. If we look at the first row of this matrix equation, you can see that we've got R1' is equal to R1 plus R2. That's the equation we had on the previous slide. R1' is just equal to R1 plus R2. And if we look at the second row of the matrix equation, R2' is just equal to R3 plus R4, and then R3' is equal to R5 plus R6. So we've managed to write this restriction process conveniently in matrix form, and we can write this as R' vector is equal to capital R matrix multiplied by R, where R is the original residual vector. And this matrix R is known as the restriction matrix, or the restriction operation. And what this does is it captures that restriction of the residuals from the coarse mesh, the original mesh, down to the fine mesh. And this is really useful for us when we're writing or interpreting a CFD code, because this is just a simple matrix multiplication. If we know what this matrix R is, we just take our current residual vector on our original mesh, just multiply it by the matrix R, and straight away we've now got our R' vector for our coarse mesh. And the other thing I want you to notice is that this matrix R is not a square matrix, and this is the key feature of the operation that allows us to change the size of the vector from 6x1 to 3x1. And of course, this matrix R, the restriction matrix, is going to depend on which cells we choose to agglomerate together. And just from these 2 simple examples you can see here on this slide, if I choose to agglomerate cells 2 and 3 together into 2', you can see that the restriction matrix R is going to take this form. But if I choose to agglomerate cells 1' and 2' together instead, you can see that the restriction matrix R has different entities inside it. The restriction matrix R is different, and it's going to depend on which cells the CFD code chooses to agglomerate. And I'm not going to go through in detail in this talk how the CFD code chooses which cells to agglomerate together. There are a number of different methods. You may have come across face area pairing, for example, where the CFD code will choose to agglomerate cells based on which are the largest areas of each cell. Or the CFD code may use methods based on which of the cells have larger matrix coefficients. There are a number of different algorithms which CFD codes can use, but for us and our understanding, we don't need to really understand that in this talk, and you can always look in the literature if you want more detail. All we need to know is that to restrict the residual vector from the original mesh to a coarser mesh, moving down a level, we're just going to multiply by the matrix R. And this equation is always going to apply regardless of which method the CFD code uses to agglomerate cells together. This equation is always going to apply, and R is always going to have the same shape. It may just have different 1s and 0 entries in it. So we've looked at the residual vector. The next thing I want to look at is actually the prolongation of the correction. So I'm not going to look at the A matrix yet. I'm going to look at that a bit later in this talk because the A matrix is a bit more complicated. Now we want to look at the correction vector, how we move that between meshes. And the difference here is that remember that we solve the correction equation on the coarser mesh, and what we want to do is move the correction delta x back from the coarser mesh to the original mesh, because then this is where we update the solution. We've calculated it here and we want to move it back. So this process called prolongation is actually in the opposite direction to restriction. We're moving delta x back to the original mesh, whereas the residual we move down to the coarser mesh. So how does this look? Well, the key piece of understanding for prolongation, which is often missed out in many sources in the literature, is when we're using prolongation, we're moving the correction to the solution field. So delta x may represent, for example, a correction to the velocity field or a correction to the temperature field, say. We'll have units of meters per second or Kelvin if we're looking at the temperature. So we're moving the solution field itself. Whereas when we were looking at restriction with the residual, we were looking at conservation imbalances. We were moving energy or newtons. We were moving the conservation of a quantity down, whereas now we're actually moving the solution field back. So what that means is we can't use that same approach of summation which we used before. We have to use interpolation because we've got a coarse representation of a field. We want to move the field back. So we're going to be using interpolation for prolongation, not summation. So we've got a key difference there. We're moving in the opposite direction to restriction, and we want to use interpolation. And as you may expect, there are of course different types of interpolation that you could use. You've got a coarse field, and you now want to interpolate the values on the finer mesh at points in between those coarse fields. There are different types of interpolation you could use, and indeed different levels of accuracy you could use. And the method I'm going to use here is called injection. And injection is a very simple type of interpolation, which is actually piecewise constant. So this is less accurate than linear interpolation. And the reason for this I'm actually going to explain later in the talk. But how this might look, for example, if you look at this example, let's say we've calculated a correction to a solution field delta x prime on our coarse mesh. This could represent a correction to the temperature field, for example, which looks like this. And we want to move back onto the original mesh. With injection, what we're going to do is cell 1 prime was made up of cell 1 and cell 2. And what we're going to do is the correction on those fields, we're just going to set as equal to the correction on the coarse field. So notice cell 1 and cell 2 are exactly the same. Both of these cells were constructed from cell 1 prime, and so we're just using the same values. The same for cell 3 and cell 4. They make up cell 2 prime, and so both of those have the same value as 2 prime, and then the same for cell 5 and cell 6. And you can see that this is piecewise constant interpolation. If we wanted to do better, if we wanted more accuracy, we would of course interpolate what the value is on these straight line segments here. That would be linear interpolation. But for this example, I'm just going to be using injection. That's constant interpolation, which isn't accurate, but there are reasons for it, which we'll see later. The key point is that actually, when we're using injection to move back to the original mesh, later, after we've done this injection, we're actually going to carry out more iterations of the Gauss-Seidel algorithm anyway. So even if this interpolation isn't very exact, this produces a high spatial frequency component to the error, because of course there's errors between the adjacent cells because of the interpolation. And so when we do a few iterations of Gauss-Seidel, those error components will be rapidly removed anyway. And so this is why we can actually use a low accuracy type of interpolation like injection. So how does this work mathematically, and can we assemble this as a matrix operation in the same way that we have for restriction? Let's use this same example problem. We have delta x1 prime, we have delta x2 prime and delta x3 prime. We know the correction at the centroid of these three cells, and we want to use prolongation to put it back on the original mesh. Now we can write an equation for what the correction is at the centroid of each of these 6 cells. So we have 6 equations, and of course delta x1 is just equal to delta x1 prime because we're using injection. Delta x2 is also equal to delta x1 prime. We're using injection. The same for delta x3 is just equal to delta x2 prime. Delta x4 is equal to delta x2 prime, and so on. We're just using injection to move between the two meshes. What happens when we arrange these 6 equations in matrix form? Well, when we do it, we have a matrix equation that looks something like this. You can see we've got delta x1 is just equal to 1 multiplied by delta x1 prime. Delta x2 is equal to delta x1 prime. Delta x3 is equal to delta x2 prime, and so on. So this is our correction vector on our original mesh, and then this is our correction vector on our coarse mesh that we've just calculated. And what we can see is this operation of injection is equivalent to multiplying by a matrix P, which is often known as the prolongation matrix or the prolongation operator. And it's very similar to the restriction matrix that we saw before. It's not a square matrix, and of course it can't be a square matrix because we need to change the size of the vector from a 3x1 up to a 6x1. So it's a non-square matrix with many 0 values. And of course in vector form we can write the equation simply as a matrix multiplication like this, which you can see here. So this is really useful for us because it's telling us that if the CFD code decides to use injection or it decides to use linear interpolation or another type, we're always going to get a matrix equation of this form where we're pre-multiplying by a prolongation matrix P, but the quantities in this matrix P may vary depending on the type of interpolation and the cells that we've chosen to agglomerate together. And this is a really useful result. And actually, for this particular example, some of you may have noticed that when we choose to use injection for prolongation, and we look at the restriction matrix and the prolongation matrix, you can see that actually the prolongation matrix is equal to the transpose of the restriction matrix. This result, equation 11, is really important. It only holds when we choose to use pure injection. If we use linear interpolation or a higher order form of interpolation, the P matrix will be different. We'll have different coefficients in there, and so it won't be equal to the transpose of the restriction matrix. But what this result allows us to do, it's really important, is it means that we only need to calculate and store the restriction matrix, because anytime we need the prolongation matrix, we can just take the transpose and we have it. And this is going to save us a lot of memory in our CFD code, particularly if we're moving between many different layers in a multi-grid method. Each time we move between a level, we're moving from an original mesh down to a new coarser mesh, we're going to need a new restriction matrix, because that's going to tell us which of the new cells are being combined together. So we're going to have lots of different restriction matrices, one for each of the levels. And by having this result available, we don't need to calculate and store the prolongation matrix. But it does mean that we have to use injection, which of course isn't as accurate when we're going back up to those original meshes. So that's prolongation and restriction. Now let's look at the A matrix. When we're moving from this original mesh with 6 cells, our A matrix, of course, has dimensions of 6 by 6, because there are 6 centroids in the mesh. We're moving down to our coarser mesh, and this mesh only has 3 centroids, so the A matrix is going to have dimensions of 3 by 3. Again, you're probably already guessing that we're going to need to do some kind of matrix multiplication here to change the size of the A matrix to get down to this smaller A prime matrix. Now, there are actually different methods that we can use to construct the A matrix for the coarse mesh. And the first method we can use is actually a more direct method, which you may have intuitively guessed, and that is to actually just construct the new A matrix directly. And what that means, of course, is that we would have to go around the matrix, evaluate all of the distances, all of the surface quantities on all of the faces connecting all the cells, and just reconstruct a new A matrix in the same way that we did for our original mesh. We would treat the coarse mesh like an entirely new problem and have to go around and evaluate all of the matrix coefficients. And the example that I've given here for thermal diffusion is that there's a contribution in the A matrix from thermal diffusion of the thermal conductivity of the face multiplied by the face area and then divided by the distance across the face. So if we were assembling a new A matrix for thermal diffusion, of course we could go around and see, now that these cells have been agglomerated together, the distance has increased, so there's a new matrix coefficient, and we would paste that in and assemble the new A matrix almost manually. And this approach is called geometric multi-grid. The reason for that, of course, is we're using the geometry. We're using the new geometry of the mesh to construct a new A matrix for the coarse mesh. But of course, even at first glance, you can see that this method is quite slow and it has quite high memory requirements, because we're going to have to go and construct all of those coefficients for all of the cells in the mesh again. And of course, every level that we go down in a multi-grid structure onto new meshes, we're going to have to repeat this process every time. This isn't a very efficient method of doing things. And actually, most modern CFD codes use an alternative approach, which is to try and derive an equation for the A prime matrix directly. And that's what I'm going to go through next. So we want to derive a matrix equation for A prime. We want some kind of matrix multiplication that's going to make it easy for us to get that without having to assemble all of the matrices and the coefficients directly. And to derive this equation, the derivation proceeds as follows. The first thing we do is that we state that in the next iteration of the multi-grid algorithm, we will be solving this new matrix equation. A times x nu is equal to b. X nu will be the updated solution vector x. And when we solve that updated equation, that's going to produce a new residual vector in the same way that we are in the current iteration. We're going to have r nu. And to derive an equation for A prime, we're going to place a requirement on this. And the requirement is that when we restrict the new residual vector, so when we multiply it by the restriction matrix R, we want this to be very small. We want it to be approximately equal to 0, because our algorithm is converging. We want to bring our residual down rapidly and fast towards 0. So with that constraint, we can substitute equation 14 into equation 15 for R nu, and that allows us to arrive at equation 16. So R, the restriction matrix, multiplied by B minus AX nu is approximately equal to 0. And of course, this quantity in the brackets will evaluate to a vector, because B minus AX will evaluate equal to a vector. And then when we apply the restriction matrix R, that's then going to reduce the size of that vector down to an appropriate size for the new mesh. And how can we proceed with this derivation? Well, we want to replace x nu with something that's going on in the current iteration. And what we're going to do is replace the new value of the solution vector just with the current solution x plus the correction delta x, which we'll be solving for. And we can also rewrite the correction delta x in terms of the prolongation matrix multiplied by delta x prime. So you can see we're using that second result that we derived earlier in the talk for the prolongation matrix and the update to the solution field. So we're going to substitute equation 18 in for x nu. So we've still got r multiplied by b minus ax nu, but we've just replaced x nu with x plus the prolongation matrix times delta x prime is approximately equal to 0. Then what we're going to do is just do some slight rearranging. Just rearrange these terms, move them around. And what I'm going to do is move the b minus ax multiplied by r, move that to the other side, and keep the r multiplied by a and p delta x on the other side. And then just a bit of simplification to go from equation 20 to equation 21. B minus AX is of course equal to the current residual vector multiplied by the restriction matrix R is the restricted residual vector R prime. And if we look on the left hand side, we can see that we've got a collection of terms. We've got RAP multiplied by delta X prime. Delta X prime is the correction to the solution vector on the coarse mesh. That's equal to the residual on the coarse mesh. And we know that these three quantities collected together must be approximately equal to the restricted A matrix, A prime. And so we arrive at the result that A prime, that's the A matrix, the 3x3 A matrix, is approximately equal to the restriction matrix multiplied by the large original A matrix and multiplied by the prolongation matrix as well. So we have a very simple result, a matrix multiplication that we can use to approximate A prime. So how does this look? How do we use that result, equation 22, in practice? And what does it actually mean? Let's go back to our example problem that we've been using throughout this talk. We've got our original mesh with 6 cells numbered 1 to 6, and we're going down to a coarser mesh, 1 prime, 2 prime, and 3 prime. And we've already worked out what our restriction matrix is and our prolongation matrix is. And we've used pure injection, so of course P is just equal to the transpose of R. So what is A prime? Well, what we need to do is evaluate that equation that we just derived. A prime is equal to the restriction matrix multiplied by the A matrix multiplied by the prolongation matrix there. And of course this is quite a tricky bit of matrix multiplication. You can always go through this by yourself and multiply the rows and columns together and work out what the quantities are. And I've already filled in the basis of what the A matrix is, where of course the 0 values are where the cells in the mesh aren't connected together. So cell 1 is only connected to cell 2, so its coefficients 3, 4, 5 and 6 in the first row will be equal to 0, and so on. But if you actually go through and multiply these results together, so of course you want the row multiplied by the column and so forth, you arrive at this form of the A prime matrix. And you can see here that it's got dimensions of 3 by 3. Got 3 elements, 3 by 3, whereas the original A matrix was of course 6 by 6, because we went from a 6 cell mesh to a 3 cell mesh. So our A matrix has gone from 6 by 6 to 3 by 3. But what are these coefficients? What's actually happened here, and what does it actually mean? What does it show us? Well, if we look very closely at the mesh, what's happened? We've combined cell 1 and cell 2 together to get cell 1 prime. And the diagonal coefficient of 1 prime, so the first row and the first column, the new diagonal coefficient is A11 plus A21 plus A12 plus A22. We've combined the coefficients together that link cell 1 and cell 2 together. We've linked the diagonal and the neighbour coefficients all together. We've clustered them together. But of course, cell 2 has not been agglomerated with cell 3, so the coefficients A23 and A32 remain unchanged. They're still there in the A prime matrix. If we move on to cell 2 prime was calculated by agglomerating cells 3 and 4 together. And so you can see the neighbour coefficients and the diagonal coefficients have been combined together. But of course the coefficient 4, 5 and 5, 4 remains unchanged because we didn't combine those cells together. So this is telling us that physically the result A prime is approximately equal to RAP. What effect that's happening when we evaluate that matrix multiplication is that we're combining the neighbour and the diagonal coefficients together when we form those new cells. We wouldn't do this in practice. In practice, we would just evaluate the matrix multiplication. Easy, and the computer can do it. But this is physically what's happening to the A matrix. It's changing size, and we've got some new coefficients there. And this approach of calculating an approximate A prime matrix for the coarse mesh is called Algebraic Multi-Grid, because we've only used algebra here. You may notice that we haven't considered the new geometry at all. We haven't evaluated any new coefficients. We've used algebra directly. And it turns out that A prime is only an approximation to the value calculated using the geometric multigrid. You could use the two approaches and compare them, and what you'd find is that the A prime matrix is actually slightly different. And of course, the value calculated with the algebraic multigrid is the approximation, whereas the geometric value is the true value. So if we use this approach, the algebraic multigrid, what's going to be the problem here? Well, it's really important to remember that, of course, when we're solving that correction equation, A prime x prime is equal to R prime on the coarse mesh, the solution, delta x prime, is only an approximation to what the update should be on the fine mesh anyway. Because when we move it back to the fine mesh, we calculate post-smoothing iterations of the Gauss-Seidel algorithm. We calculate a few more iterations to smooth out any high-frequency component of the error anyway. And so that means that delta x prime doesn't need to be exactly correct anyway. It can be an approximation, and it follows that it's therefore also fine to use an approximation for A prime. The better approximation we have, the better, but it's not essential that this A prime matrix needs to be exact. It's slightly wrong when calculated using algebraic multigrid, but that's actually okay. And if we want to apply a correction to this approximation, you can find that in the book by Greenshields and Weller, and I've got that linked in the description to the exact section that you'll need if you want to find the approximation. You can find that in there, and I would definitely recommend reading it. So just a quick summary of what we talked about today. We've thought about how the various vectors and matrices can be transferred between levels when we use a multigrid approach, and the method of transferring the residual vector R from the original mesh to the coarse mesh is called restriction, and we carry this out in practice just by formulating that matrix R and then just multiplying it by the vector R. And physically this is equivalent to summing the residuals, which we can do because in the finite volume method the matrix equations physically represent conservation over regions of space. And once we have our solution update delta x prime on our coarse mesh, we want to move it back to our original mesh so we can update the solution, and this process is called prolongation. And there are different types of interpolation that you could use for prolongation, but a common choice is to use piecewise constant. And even though this isn't very accurate, it gives us the very useful result that P is equal to the transpose of the restriction matrix. And the A matrix is perhaps the most challenging of the vectors and matrices to transfer to a coarser mesh, and we can actually just approximate it by using the algebraic multigrid. And this is really useful for CFD codes because it's more efficient for us when we're transferring between multiple levels and we're not having to construct new A matrices every time we go. So that wraps up part 2 of my discussion on the multigrid method. Let me know in the comment section, did you find this video useful? Did you like the use of examples? And do you feel like now you have a better understanding of actually how the multigrid method is moving between levels in the grid? I'd really recommend you actually having a go for yourself, maybe construct a few simple meshes and see if you can work out what the restriction and prolongation matrices are as you move between those levels. I'm sure you'll find that really helpful. Until next time, thank you all very much for continuing to support the channel. I do really appreciate it, and I'll see you in the next video.